Do-it-yourself Foucault pendulum. This is the second video of a 3-video series. The last one covered the math and science, or math and physics, of pendulums, specifically the Foucault pendulum. This video will show you how to make your own do-it-yourself style, and the third video in the series will show my results. Now, if you have a pendulum swinging back and forth, and the pendulum is allowed to swing in any direction, what you might find is if you allow it to swing over time, it may change direction. So the goal of this project is to accurately measure the change in angle of the plane of the pendulum's swing. And you're going to calculate the period of precession. So there are 7 keys to a successful Foucault pendulum, and here they are in order of importance. Accurate measurement of the swing plane angle across time, the precision launch with a burned thread, a very long string or wire with a bias-free attachment, a heavy or dense bob with a thin string or wire, repeated trials with a variety of launch azimuths, and then small deflection, which means a short swing arc, and then lastly a still air location. So really all these things are important, but the most important things are at the very, very top of the list. So what I've decided to do is to divide these things up into steps. And the very first step, which I'm going to call step 0, is to make the measuring tool. And then let's take a look at these 7 items. These 3 I'm going to call make the pendulum. These 2 we're going to call it step 2, launch it. This one is going to be step 3, measure the change. And then lastly, you're going to do step 4, which is repeat. Now, after you've done all these things, we want to analyze our results. So that'll be the last part of our video. So step 0 is to build the measuring tool. So to make a precession measuring tool, you need a lazy Susan, a fabric tape measure, a yardstick or a meter stick, some string, and some tape or glue. So what you're going to do is you're going to take a lazy Susan and wrap your fabric measuring tape around the circumference. All right, so there's your measuring tape just wrapped around the circumference, and I used rubber cement to secure mine in place. You're going to mark the exact center of rotation of the lazy Susan, and you want to make sure the bearings are well lubricated. You want this thing to rotate very, very smoothly like butter. Then you want to record the exact circumference of your lazy Susan. This will be very important in the later calculation. So with your yardstick or your meter stick, you're going to attach it so that one end is exactly at the center of rotation, and you want to draw a black line down the center of your yardstick. All right, this line will be what we will align to our pendulum. Now this probably isn't going to stay in place, so you may want to brace it with some string and tape. You don't want the yardstick to wiggle left or right. In other words, if you move the end of that yardstick 1 millimeter, you want the lazy Susan to rotate smoothly. All right, because it's going to be very, very important that we align this yardstick with the swing of our pendulum. All right. Now, because it'll be hard to measure when the swing is sort of above the lazy Susan, it might be nice to have some play. In other words, try to set your yardstick up so that it hinges at the center of rotation. So if you have a little bit of vertical play, that is actually beneficial. You don't want any horizontal play at all. You want it to rotate as one unit. Now, how are we going to actually do the measurement? Well, it's best to use like a little piece of thread and a piece of cardboard. We're going to make it a hairline cursor, almost like a slide rule. So this is what that might look like. There's the hairline cursor right up against the measuring tape, and then you want to mark your camera's location with an X, and have that X be aligned with the center of rotation and the hairline cursor. In other words, the camera is going to be looking at the measuring tape at a 90-degree angle. Now, why is this important? So let's say you take Joe and Reggie, and they're both trying to measure the length of this clownfish. So Joe, according to his perspective, Joe says, well, that's about 9 inches long. And Reggie says, well, you know, according to my perspective, it's about 5 inches long. And they're both right. That's what it would look like from their perspectives. But we all know that the clownfish is approximately 6 inches long if you look at it 90 degrees to the measuring device. All right, so that's going to be very important that that green line is actually intersecting the ruler at a 90-degree angle. So we have a very, very clear indication with that hairline. So that was the measuring tool. Now we're on to step 1, build and mount the pendulum. So we're going to start off with a still air location. And this is something with a high ceiling. You really need a location with a high ceiling. Short pendulums just simply will not swing for very long. So here's an example. If you have a big garage like this with a bunch of toys in it, if you close those garage doors, then you might be able to use this location for your pendulum. Now you might say, well, won't those rafters get in the way? Well, with our pendulum, we're not going to have it be wildly swinging. Okay, we're not going to have a big swing to this. So if you have a nice gentle swing, it will fit between those rafters. All right. If you have a barn and you close the barn doors, that might work really well. If you have access to a gymnasium or even an airplane hangar, that might work as well. Personally, I'm going to use a garage, my dad's old garage, and I've got about a 14-foot height that I'll be able to have on my pendulum. So here's a pendulum bob. This is a professional, like a surveyor's bob. And there's a couple qualities that this thing has. One is it is symmetrical radially. In other words, it's like a cylinder or a cone. And then the other one is that the pointer at the very bottom is centered below the center of mass. So let's examine these in turn as we explore different ways to make a pendulum bob. Now, one way of making a bob is to use just a retired bowling ball, but these max out at around 16 pounds. Another thing, if you want to go heavier, and this is just an idea, there's tons of ways of making a pendulum, but if you take a 5-gallon bucket and you fill it up completely with concrete and water, that will be about 100 pounds of weight for your pendulum. So if you don't want that much weight, well, fill it up halfway. Okay, so just be careful if you go with a really heavy bob. What I'm going to do personally is I'm really concerned about my 14-foot height being, too short. So I'm going to make a really heavy pendulum bob. So I've got these Soloflex hand weights, and it's a pretty ingenious design. The centerpiece is essentially a piece of pipe with holes drilled in the edge or in the ends, and the hand grip is just a sleeve of rubber. All right, so that just slides right off. It's not attached permanently. So if I take that pipe and I stand it on its end, and I only put on one end cap, then I can stack up 120 pounds of plates, and that's going to be my pendulum bob. All right, so let's examine the qualities that we need for our bob. One is that it needs to be symmetrical radially. And what that means is no matter the direction of swing, it's going to have the same drag. Now, we talked about drag in the last video, so this is very important. You minimize drag. But what's important in this video, in this exploration, is that the drag is at least constant. All right, so no matter what direction it swings, it'll have constant drag. The next thing is the pointer needs to be centered below the center of mass, and that's important because if the bob is swinging in a different direction or if the bob spins, then the pointer is going to be pointing at a slightly different angle, and that's going to mess up our results. We're going to think we're having a change in angle where there really might not be a change in angle at all because the bob just rotated. So that pointer really needs to be below the center of mass. All right, so let's examine this first attribute. So here's some guys, they literally made a Foucault pendulum at the South Pole, and they did it when this one section of the station was under construction. It's called, I think, the beer can. So it's this cylindrical structure. I think it has a stairway in it. And this was their first attempt at the hanging weight, and I hope you can see that this is not going to work out. In fact, it was a big fat failure because that did not have the same drag when it was swinging in different directions. All right, so they improved their design, and then they had this thing swinging horizontally, which has got the same drag in all directions. So that is radially symmetrical. That's what you want to aim for. And the next thing is the pointer below the center of mass. So in reality, your bob will probably not be perfectly symmetrical. All right, so if you spun your bob while it's suspended, you'll probably notice a little bit of wobble at the bottom. So what I would recommend is that if you attach a little metal plate, and it doesn't have to be a big, something big. It could be as simple as a couple of paper clips. But if you add some piece of steel to the very bottom, and then you just stick a magnet to it, and there's this set of magnets called pushpin magnets. So it's designed to look like a pushpin, like a thumbtack for a corkboard, but it's just got a magnet. So you stick that to the plate, And then what you do is you test and you spin it around, you try to find where the center of mass is, and then you just very slowly adjust that push pin so that it does match up with the exact center of mass. All right. And again, the whole point of this is that as your pendulum is swinging, you want to be able to align that yardstick or your meter stick. You want to align not just the meter stick, but the black line on the meter stick so that it is exactly lined up with the center of mass at the bottom. So how are you going to support this? Well, if you've got a really heavy bob, you may think, well, I'm going to use a piece of rope or some chain. Well, the rope is going to have a lot of drag, so that really is going to slow your pendulum down. And the chain is also going to slow it down. Also, it has a lot of mass to it. So you really want all your mass to be in the bob itself. So I wouldn't recommend that. I would recommend that you explore fishing line. Now, you got to be careful with fishing line because there are various test strengths. So, for example, this, it's a pretty standard piece of fishing line, very, very inexpensive, but it's 30-pound test. All right, so if you've got a fairly, like let's say you're going to go with the bowling ball, well, then this might work just fine. All right, my pendulum bob is going to be 120 pounds, actually 120 pounds plus. So I'm going to go with 200-pound test. And this isn't actually fishing line, this is actually leader. So this is really thick stuff. Well, I mean, it's thin, it's a lot thinner than a rope, but it's thick in terms of fishing line. Now, the next thing you want to do is be careful with how you attach it to your ceiling. All right, so here's an example. This actually is from my swing set. Is this an unbiased attachment? So if you were to tie a knot on this thing and have it swing left to right, we'll call that the north-south swing axis. Well, it's gonna swing sort of in that eye, right? But if it starts swinging backwards and forwards, which I'll call east-west, then it's going to be swinging using that bearing, right? That swing set bearing. And that's going to change, like it's going to be more likely to swing on this bearing than the east-west. Than north-south. So this is really going to mess up, it's going to mess up your results because this thing wants to swing in one direction instead of the other direction. All right, so that's really going to mess up your results. So you really want to have a bias-free attachment. Now, what I'm going to do, since I'm using fishing line / fishing leader, is I'm going to be drilling a very thin hole in a piece of wood, and I'm going to thread the fishing line through this hole. All right, so it'll be able to swing in all directions, and it's going to be able to swing in all directions equally well. So when you finally suspend your bob, you've got the thing all set up. You have to wait for your bob to completely come to a complete rest before you align your lazy Susan. So you want that center point of the lazy Susan to be exactly underneath the center of mass of your bob. Even if you're off like a 1/4 inch or a couple millimeters, that's going to mess up your readings because it's going to change your angular results. All right, so that was step 1, building and mounting the pendulum. On to step 2, tensioning and launch. All right, so pendulums tend to work the best, at least the math works the best, with a very small deflection. All right, so if you have a very wildly swinging pendulum, they tend to decay very, very quickly. Also, it's hard to measure the angle. So we really want to pull this thing back a maximum of 10 degrees. And that orange triangle over the left, that is actually to scale. So that is literally a 10-degree angle at the top of that triangle. So that's sort of what we're going for. And if you do a little bit of math, if you know the height of your pendulum, you take the tangent of 10 degrees, do a little bit of math, it ends up being 0.176, so around 18%. So your deflection should be around 18% or less than 18% of the height of your pendulum. Now the next thing is the thread that is holding it back. So again, all pendulums need to be started by pulling them back and then letting them go. So over on the left-hand side of the screen is a free body diagram. So if that pendulum bob is at rest, in other words, we haven't cut the thread yet, all right, it's just waiting for us to launch this pendulum, then since that bob is at rest, we need to have all 3 of those force vectors balance out. So you got the support wire at an angle, the thread is pulling it back, and then the weight of the bob is pulling it downwards. So if you kind of redraw these 3 vectors, they need to all balance each other out. They need to all cancel each other out. All right. So if you have a 10-degree deflection, the math is exactly the same as before. It's tangent of 10 degrees, and we end up with 0.176. So the tension of that thread will be, again, about 18% of the bob's weight. So if you know how heavy your bob is, take 18% of that, and that will be the thread tension. All right, and this is important to know because what kind of thread are you going to use? Now, nylon thread, specifically size 92 nylon thread, is very strong, 15-pound tensile strength. It turns out it's not strong enough for my bob because my bob is 120 pounds. So I may end up using 2 or 3 strands of this. All right, so just be careful that you go in with open eyes. So do the math first. All right, now you may run into a problem if you tie this thing off, tie this thread, but the mounting point for the thread is really far away. You may end up with sort of a Newton's cradle type thing. In other words, it's going to be a secondary pendulum effect. Your bob may want to swing left and right, or sort of forward and backward into the screen, as we see here, if your thread is too far away. So if it matches your situation, just let your pendulum stabilize. Don't pull it back with the thread and then immediately try to launch it, because your pendulum will have some residual motion to it. So you really want your system to come to a complete rest before you launch it. All right? Or you can get around this. Better solution would be to make a strong movable support that's close to your pendulum bob, and then tie your thread to that. So in this illustration, we have a museum in Europe, and this guy is demonstrating the Foucault pendulum. Now you can see the walls are really far away. So what he's got here is a movable support that just sits on the floor, but it probably has bricks in it, so it weighs a good bit. And notice the thread that he's using is only a couple inches long. All right, so that'll stabilize very quickly, so that you can get on with your demonstration. Now, so here's a good example. You can use another 5-gallon bucket, fill it full of rocks or fill it full of water. That'll make a nice handy movable support that you can put very close to your bob, only with a few inches of thread. All right. Now, how are you going to launch it? The best way of launching these things is with fire. Okay. You don't want to use a pair of scissors. You don't want to release it by hand. You don't want there to be any sideways motion or any even vibration. You want this thing to be launched with precision. So this is called a precision launch, and it's usually done with fire. All right, so if you burn through that thread, you are not imparting any sideways force. Okay, so take your match and light the thread, and then launch the pendulum that way. All right, so that's tension and launch. On to step 3. So step 3 is measuring the precession. Measuring the precession. So that's why we had that precision measurement tool that we made. All right. So again, we have this thing swinging back and forth. Hopefully that the angle will change over time. How do we measure that? Well, remember, we have on the Lazy Susan, we have stretched a measuring tape. We've glued it to the edge. We also have made a hairline cursor using some cardboard and some thread. And we've also had X marks the spot, so our camera is in a consistent location where we're going to take our photographs. All right, so what will the camera see? All right, so this may be an illustration of what the camera might see. So, if you're using a digital camera and you take a picture, it'll have a timestamp to that photo. And then as we let the pendulum go, it's going to swing at a slightly different angle. The measuring tape's going to move, and then we could take another picture. All right. Another thing you also want to record is whether your Lazy Susan is turning clockwise or counterclockwise, or whether the swing angle is turning clockwise or counterclockwise. All right. So here's a pair of photos, and we're not going to take these readings. This is just an illustration. All right. But you just want to have 2 cautions. One is if you take the photos too close together, you might not really be able to record precession with any kind of accuracy. So there may be very little precession or almost no precession at all. But if you wait too long, the swing might have degraded so much that it's barely swinging, and it's really hard to measure the swing angle when you have very little swing to your pendulum. So you just want to balance these 2 considerations. So I'm just going to use some made-up numbers for this. So you take your 2 timestamps and then you subtract them to find the difference. So you have the difference in minutes and seconds. So we don't really want minutes and seconds. We want like decimal minutes. So divide the seconds by 60 and then get a decimal and then just tack that onto the minutes. So in our example, 6.63 minutes, all right, T sub m. You also want to take the two measurements using that thread that on the cursor, and then just subtract them to find the difference. So our difference, or our delta, in this case was 2.5 centimeters, and then our T sub m, or the time, the difference in time in minutes, was 6.63. All right, and your numbers are going to be different than mine. Now, you're going to plug this into a proportion. You're going to plug these numbers into the proportion so that you can compute the precession. So I want to explain exactly why this proportion works. So D over C, well, D is the amount of the difference in the two measurements, whereas C is the circumference. So in other words, this is a fraction. So you know a fraction, in elementary school we learned fraction is parts of a whole. So the D is the part. We've moved the lazy Susan a little bit. C is the whole. That's the whole circumference. All right, parts over a whole. T sub m was the amount of time it took for us to move that little bit. And then the P sub m is going to be the amount of time it'll take to move a complete circle. In other words, that's going to be the period of precession. So if we rearrange this, we have P sub m equals C times T sub m over D. All right. Now, normally we don't express precession in minutes. We normally express it in hours because it's usually longer than a day. So if we divide by 60, we get P sub h, or precession in hours. All right. So that's our final formula. All right. And again, you want to record whether your precession is clockwise or counterclockwise. You always want to record that in your notes. So that was step 3, measuring precession. Step 4 is going to be to do repeated trials with a variety of launch azimuths. So this is just an exaggeration. So let's say you have your Foucault pendulum and somebody says, oh, well, the reason why your pendulum changed direction was because there was a moving current of air. So there's always going to be some doubt. Did it really move on its own, or was it moving because there was air blowing on it or something? So you can solve this problem by having your repeated trials launching at different angles. So for example, you may want your pendulum to swing east-west. So you launch it, obviously you have to launch it at one side or the other, but then have another one where it's going northwest or southeast, right? Then have another one that swings north-south, and then have another one that swings northeast or southwest. And each time you're varying, you're not launching it always from the right-hand side. Sometimes you're launching it from the left, sometimes from the right, and you want to vary the launches and vary the azimuths. All right, so this actually will cover 8 azimuth. Well, it says 8 azimuth pairs. It's 4 pairs, 8 azimuths. So on the flat Earth side, there may be some some explanation that says the sun is moving by. Now, when the sun moves by, maybe it sets up a vortex. Okay, so maybe you've got this vortex that's induced by the sun. So one thing that you might want to do to kind of explore to see if this is really happening is you may want to try to have other trials, AM versus PM. So for example, here we are in McShmursville, USA, and so this is probably around sunrise for McShmursville. So maybe you test it out in the early mornings. Now the sun hasn't come by yet, So all right, so now the sun's by. There's a solar noon. Okay, then you do it again. You do it in the afternoon. Okay, so maybe you get a different effect in morning versus afternoon. Maybe that will test the idea that there is a vortex set up by the sun over the flat Earth. And there's another consideration, and one is the calendar date. So for example, if you're near the June solstice, the sun is going to be traveling above the Tropic of Cancer. So if you take a look at the little coffee cup over there, you've got these vortices because the sun is traveling very near. So right now the sun is nearer to McShmursville, but maybe when the sun is further away at the December solstice, it's above the Tropic of Capricorn. Well, maybe if you test it again, well, maybe the vortex has a weaker effect. So that may affect your results. So you want to record what's the date. Because you're going to be really trying to figure out if the flat Earth model works or if the globe Earth model works. All right. So you do want to have repetition launch azimuths, and then bonus points if you do it with a variety of AM, PM versus a variety of dates. All right, so lastly, we're going to come to our analysis. And this really is very straightforward because on the flat Earth, they say it's stationary. The globe Earth, the whole globe is turning, once a day. So our analysis is going to be pretty easy. But before we go over the analysis, let's go over two misunderstandings. One of them is that Foucault pendulums are all faked. And, well, guess what? That might be true. You may believe all Foucault pendulums are faked, except for the one that you just built, right? The way you put this to bed is by making your own. But you'll probably see, if you watch enough of these videos, if you go to enough science museums, you'll find out that there's no way that they're faking all of them. Some of them do have a mechanism to keep them going, but you could put this to bed by making your own. The other misunderstanding is that Foucault pendulums are supposedly starting. They're supposed to start swinging by themselves, and I'm not really sure where this came about. The only time you have a pendulum that starts itself swinging is if you have an earthquake. In fact, the original earthquake detectors used a form of a pendulum and to detect where the direction of the earthquake came from. So pendulums don't start swinging by themselves. Certainly not Foucault pendulums. You have to pull them back and launch them. All right. So let's take a look at our analysis on the flat and stationary Earth. So the easiest analysis is really straightforward. No precession is expected. If the Earth is flat and stationary, there's no reason for a Foucault pendulum to swing at any different angle. If you start setting it swinging, it should just swing in that direction, period. All right. But if you do acknowledge that the pendulum is going to change angle, well, maybe it's because of this vortex effect. But then that vortex effect should depend on where the sun is. Like, did the sun just go whizzing by, or is it in the afternoon, or is it in the early morning, which means the sun hasn't been by for 18 hours or so. So you should notice an effect that changes by time if it's because of the sun's vortex. You should also notice the effect changes by date. All right. So if the Earth was flat and you do acknowledge that the change in angle is going to happen, well, this change in angle should vary by time and date. All right. Now let's take a look at the globe Earth. Well, the precession will vary only by latitude. In other words, it doesn't matter AM, PM. It doesn't matter season. The only thing that matters is your latitude. All right. That's what the globe Earth predicts. All right. So in our last video, we covered a whole lot of math. All right. We covered a whole lot of math. And we derived this formula. All right. That formula is the length of a sidereal day in hours divided by the sign of your latitude. All right. So T sub E is the sidereal day. So you can just plug in 23.934 and you'll get pretty good results. So your question is, does your data match the flat Earth model, or does it match the globe Earth model? Again, in the globe Earth model, you're going to have clockwise precession in the northern hemisphere, counterclockwise precession in the southern hemisphere. And it doesn't matter what the date is. All right. So your mission, if you choose to accept it, is to make and test your own Foucault pendulum. And it would be great if you can give your results in the comments. And if you could record your own videos, record your own Foucault pendulums, that would be great. Give the links and I'll be happy to share them. So, as always, please be kind to one another. Thank you.